Ladies and gentlemen, how are we this fine Tuesday morning, evening, Monday evening, or whatever time it is across the world? Can I just get someone to give me a thumbs up to otherwise confirm that you can hear me clearly and see the screen? Thanks, Nathaniel. I'll take that hand wave as opposed to a thumbs up. Bright and sunny here. Thank you, Fred, because it's not bright and sunny where I am. Okay, ladies and gentlemen, once again, thank you for turning up to one of our Ascendo Reliability webinars. Now, in the webinar admin or the webinar page itself, you should have access to a workbook, a PDF workbook. It's editable, and that's going to contain all the information of this webinar. There's room, I should say, in the editable PDF for you to be able to take notes as you seem fit, but everything we talk about will be included in that workbook for future reference. So today, I'm going to talk about discrete distributions. And before we go into, thanks for that comment, Fred, regarding that workbook. So regard to what discrete distributions are, we're going to go through a couple of scenarios to paint the picture first. Because discrete distributions are really useful for helping us, as the title suggests, do things like fleet planning and spare parts analysis. And what we're going to cover today is a relatively high-level introduction to discrete distributions and how they can help us essentially do logisticy stuff. So let's paint the scenario first, which is always a really good idea because that motivates us to want to understand these tools, these things, these concepts to help us answer these questions in day-to-day life. If we learn the tool first, we're not nearly as motivated until we learn why it's important to have that tool in our toolbox. So let's look at a scenario which is based on a military vehicle, one like this, an armored vehicle, which is very slowly coming up on the screen right now, very discreetly at this point in time. So this is an armored personnel carrier. It's as the name suggests, it's an armored vehicle. The idea is that it's supposed to be able to transport soldiers across the battle space in relative protection so they can get as close to their objective as possible before they need to start engaging. Very useful tool on the battlefield. And as is the case for lots of machines like this, they often operate in fleets. You, as a rule, never have an armored personnel carrier operating by itself. And when we deal with fleets, we often use this thing called operational availability. Operational availability is essentially the probability that if I walk up to any one of these APCs, armored personnel carriers, there's 90% chance that it is available. And available means that it is either has never failed in its life, or it is or it's never failed in its life, or it has failed and it's repaired and it's now back in a functional state. So in this case, let's assume that this APC has an operational availability of 90%. I can also see, just as a slide aside, some comments in the chat about the workbook. I'm sure Fred's going to give you the details on how to get that workbook as soon as possible. So in this scenario, let's just say we have a fleet of 10. And this is not uncommon for an infantry company, a mechanized infantry company. They usually have around about 10 armored personnel carriers. And let's just say that we need exactly 9 of them to be fully functional to conduct a mission. And that's our go, no-go criteria. If you have 9 ready to go, we should be able to launch. And because you have an operational availability of 90%, and we have a fleet size of 10, then by rights, we should always have exactly 9 APCs ready to go. Well, life, unfortunately, isn't quite like that. The reality is that there's a finite chance that every single one of these vehicles could be available or unavailable. And that's because there is a 90% chance that any vehicle is going to be fully functional, There's a 10% chance that any vehicle is going to be unavailable or non-functional. And so what that means is we can only deal with probability in this case. We can never deal with absolutes because failure is a random process. And we will have to assign a probability to all possible numbers of available vehicles. So we have a fleet of 10. It is theoretically possible for none of them to be available. It's theoretically possible for all 10 of them to be available. It's possible for 4 of them to be available, 6 of them to be available. And so for every number of possible available vehicles, we need to assign a probability of them being available. But how do we do that? How do we work out the probability of, as the original question asked us, what is the probability of us having exactly 9 vehicles available? Well, this is how we go about doing it theoretically. So we're going to start off with one of many scenarios where we have 9 functional vehicles or 9 available vehicles. So let's just say you walk up to this the fleet of 10 armored personnel carriers, and the very first 9 APCs you select or touch are all fully functional, as indicated by this row of green vehicles. And we know that there's a 90% chance of this occurring for each individual time we approach one of these vehicles and do a test and otherwise make sure it's good or no good. And so the probability of the first 9 vehicles being available is simply the operational availability to the power of 9. It's just 90% multiplied by 90% multiplied by 90%, 9 times. And then remember, this is a scenario where we find exactly 9 vehicles available. It means that in this scenario, the 10th vehicle is unavailable. And the probability of that vehicle being unavailable is 1 minus the operational availability. And so we have now got an expression that gives us the probability of the first 9 vehicles we select being available. But as you and I both know, there are plenty of other scenarios where there's plenty of other selection scenarios or combination scenarios or permutation scenarios where not exactly 9 vehicles are available. In fact, there is exactly 10. In some case, in the first scenario, we happened to select, it happened to be the case that the first 9 vehicles we selected were available and the 10th wasn't. It happened to be the case in the second scenario that the first 5 vehicles were available. The 6th vehicle was unavailable, and the last 4 last 3 were not, or whatever the second scenario is on the screen. So we have 10 different ways we can walk up to our fleet of 10 APCs and going through a process of essentially random selection, come away with 9 APCs functional. And so this is very useful, even if this seems like statistical gobbledygook or mathematical torture. The reason being is that we can simply, as a general rule, multiply the different ways we can select 9 functional vehicles, multiply it by the operational availability to the power of 9, and multiply that by 1 minus the operational availability to give us the probability of exactly 9 vehicles being available. In this case, it's 38.74%. So this gives us the exact probability that 9 vehicles are available. So a question for you guys, does that align with expectations? We have a fleet of 10. We have an operational availability of 90%. I perhaps rhetorically suggested at the start of this little exercise that we have a fleet of 10, operational availability of 90%. That should mean we should always have 9 vehicles available. Does anyone have any comments about whether this aligns with your expectations, or if it's exactly what you'd expect, or if there's something really weird going on that up until this point you didn't think was a thing? Any questions, any comments about what we have just looked at so far? None. I'll assume, Nathaniel, that your hand is still raised from my request to raise a hand if you could hear me and see me clearly at the start of this webinar. Thank you very much. Okay, so it turns out that if we have a fleet of 10 vehicles, and there's a 90% chance that any one of those vehicles will be available or functional, we can't guarantee that we'll have exactly 9 vehicles available. We have to go through this process, this formalism. Sorry, Nelson, I can see that your comment is that 38% is in no way 90%. You're absolutely correct. Oh, sorry, now there's a couple of comments coming through. It could be 10 out of 10 as well. Should we add that probability? That's a great question. I'm going to ask you to hold that question. So if I go back, I'm going to come to that question. I'm going to answer that question very, very shortly. But if we go back to this scenario where we're focusing on finding the probability that exactly 9 vehicles will be available, we come up with this general approach where we simply multiply the number of ways we can order X functional or available vehicles, and then multiply that by the probability the first X vehicles are functional, and multiply that by the probability the last X vehicles are non-functional. And when we do that, this is what we get. The probability mass function for our APC fleet problem. Now, the question that was asked by, I think, Mahendra, was that it is possible that 10 out of 10 vehicles could be available. And that is exactly what we see. So there's about a 38% chance that 9 vehicles will be available. There's about a 35% chance that 10 vehicles will be available. And as we start going down, you can see there's about a 20% chance of 8 vehicles being available. There's about a 7% chance at 7 vehicles being available, and the columns go lower and lower and lower, all the way down to 0, which still has a teeny tiny column. You just can't see it. It's very, very small. So this is what we call a probability mass function for a discrete random variable. And in this scenario, the generic version of that approach we came up with, where we essentially multiply the different number of ways we can select 9 functional vehicles by the probability of those first 9 vehicles being available, multiply by the probability that the remaining 1 vehicle is unavailable. This is the equation that represents that generic approach. We'll go through it, and I know it's a little bit complex and perhaps intimidating, but part of this webinar is to teach you how to employ this equation in the real world in a way that's going to be simple and straightforward. Now, the very start of this equation has this weird symbol over here, and that is actually short form for that little fraction you can see in the top left-hand corner. And that too involves some weird symbols. It has the exclamation mark or the exclamation point, which essentially means that for all the numbers that it applies to, we multiply it by, for example, n factorial or n exclamation mark means that we multiply n by n minus 1 by n minus 2, all the way down to 1. Now that's just for reference. There is no need for you to ever evaluate these equations by hand, but you do need to know where it comes from. So don't forget, you have a workbook, which if you don't already have, is going to be coming very soon, which has all this stuff in there. So you don't need to furiously write this stuff down. And the reason why we have this confusing combination of symbols at the start of this equation is because this represents the different ways we can select 9 functional or available vehicles. The second part of this equation is simply the probability of finding the first X or the first X vehicles available in this case. This is you might recall in our little example, we're looking at the first 9 vehicles being available, so X was equal to 9. And as opposed to the letter P, we were using operational availability. P just simply means the probability of it being functional, successful, whatever it is you want to see in the things you're selecting. This last term over here essentially gives us the probability that the remaining vehicles, the remaining things we're selecting are unavailable or unsuccessful, or whatever it is that you don't desire. And so this probability mass function becomes very, very useful. And this P here represents what we call the probability of success in each trial. And the term trial has a very statistical pedigree. Trial is used to describe most experiments, especially where we have one of two possible outcomes. So for example, a coin toss is an example of a trial, and perhaps tossing a head is considered success, and tossing a tail is considered the opposite of success, unsuccessful or unsuccess. And so each one of these scenarios where we essentially approach a random experiment and there's one of two possible outcomes is usually considered or called a trial. Now, in the case of our APCs, the act of me walking up to an APC and turning the key to see if it's available or not is a trial. There's only one of two possible outcomes. It's available or it's unavailable. It's functional or it doesn't work. And so the generic term for scenarios where there's two possible outcomes is trial. And in this case, for fleet planning, we're talking about availability. So this is our probability mass function. Now, you'll sometimes see it be a bit more formal than that, where we have this perhaps confusing term represent or be used in addition to the probability mass function equation. And this little expression here, probability that capital X is equal to lowercase x, is the way statisticians and professors and people who write textbooks summarize a statement like the probability that some random variable x is equal to a specific value lowercase x. So the uppercase x is often essentially our random variable description. So in the case of our APCs, uppercase x represents the number of available APCs. And the lowercase x represents a particular value we're interested in. So perhaps it's 9. And another way of summarizing this further is to represent all this gumph with a lowercase f followed by lowercase x in brackets. These are all different ways of summarizing probability mass function for a discrete random variable. So let's go back to our probability mass function for our APCs. And you can see here that we have now summarized the probability of certain numbers of vehicles being available at any particular point in time. So let's just say, for whatever reason, we are driving our vehicles really hard, or maintenance is taking a long time, or they're just unreliable. And instead of our operational availability being 90%, it now drops to, let's just say, 16.6% or 1/6 of 100%. And this is the probability mass function we get when that happens, when we have a very low availability. You can see that as opposed to us having 38% chance of there being 9 vehicles available, it's a lot more skewed towards 0. And so if you're asking yourselves, that's all well and good, but if I need to take this webinar and go back to my work and solve a problem where I'm trying to work out how many available systems I have out of a fleet of N, then the way you do that is use this Excel function here. The reason why we can use this Excel function is because this probability mass function is the probability mass function of a well-known distribution called the binomial distribution. Now, binomial distribution quite literally means two names or two states, and it refers to those trials we were talking about where you conduct a number of trials, in this case, walking up to APCs, and there's one of two possible outcomes for each trial. So if you need to go away and work out what the probability of exactly 9 APCs being available out of a fleet of 10, given an operational availability of 90%, you simply use this Excel formula and it will give you that answer. Again, you don't need to furiously write this down. It is included in that workbook. And so this becomes a very powerful tool when you're doing fleet planning. But of course, you might recall that we are not just interested in exactly 9 vehicles being available. Before we do that, let's go back and review this whole concept of discrete random variables. Now, people who turn up to my webinars and do my courses are very familiar with this hand here. This hand represents a random process. It summarizes different factors that influence the uncertainty we get in seemingly identical scenarios. For example, if we have 10 identical engines and they're used in exactly the same way, in exactly the same factory, with exactly the same maintenance crew, with exactly the same environmental conditions, we know that there's still lots of factors that we can't easily incorporate or easily understand that mean that all those 10 engines will fail at frustratingly different times. Now, time to failure is an example of a continuous random variable because that engine can fail on any one of an infinite number of possible failure points in time ranging from 0 to infinity. But discrete random variables are a lot more constrained. So for our APC fleet availability scenario, we were dealing with a discrete random variable because our random variable X could only be an integer value ranging from 0 to 10. There's not an infinite number of possible values. And even if there were, it's still possible to be a discrete random variable if they're countable. So you can see here the fundamental difference between a continuous random variable and a discrete random variable. You will have, so those random variables can only exist at certain values. And in the world of reliability, those discrete random variables that we're most interested are those that can only be integers. For example, the number of failures we experience in 1 year, the number of APCs that are available, all those sorts of random variables that are related to those two examples are discrete. Let's go back to our availability problem. Remember, we could launch a mission if we knew that at least 9 vehicles were functional or available. So what we looked at so far was working at the probability that exactly 9 vehicles were available, which, if you remember, was about 38%. Now, that's great. We can launch when we have 9 available vehicles, but as Mahendra pointed out, it's actually possible to have 10 functional vehicles. So there's actually a greater than 38% chance we can launch our mission. So let's go back to our probability mass function for our binomial distribution based on our APC fleet. And we're going to introduce a different probability function called the cumulative distribution function. And if you saw what happened in that little animation, essentially what we do is all those columns which represent the individual probabilities of specific numbers of APCs being available, we sort of stack them up in a cumulative way. And you can see those columns have simply moved up. And because it's only possible for up to 10 vehicles to be available, all those columns need to sum to 1. And this is really useful because the cumulative distribution function helps us work out whether we could, or what the likelihood of us being able to launch our mission is. Now, the CDF, or the cumulative distribution function, doesn't actually get represented by those columns. It has to be represented by a curve or a bunch of curve segments. And this is what it looks like. And this tells us, for example, the probability of having 8 or fewer functional vehicles is 26.39%. So we simply go across to 8, go up our CDF curve until we hit either a red line or a red dot. And we say, okay, it's a 26.39% chance of us having 8 or fewer vehicles unavailable. And those are the conditions for us not being able to launch our mission. Therefore, the probability of having similarly, the probability of having 9 or fewer functional vehicles is 65.13%. And the probability of having 10 or fewer functional vehicles is 100%, because that includes all possible numbers of available vehicles. So to answer our question, what we have to do is from 100% select the CDF evaluated at 8 to calculate the likelihood of 9 or more vehicles being available. So in this case, we can work out that there is a 73.61% chance of us having 9 or more vehicles available if we have a fleet size of 10 and an operational availability of 90%. It's a question for you guys. Remember, the start of this lesson, I started asking the rhetorical question, fleet of 10, what would you expect in terms of number of available vehicles if the operational availability is 90%? Turns out that there's only a 73.61% chance of having 9 or more functional vehicles. Does that align with expectations, or does that challenge some presumptions you might have had about fleet availability? Please feel free to type your comments in the chat window or pose it as a question. How can we calculate the availability? Okay, I'm going to assume that that person, anonymous attendee number 1, is referring to trying to work out the probability that any one of those vehicles has 90% chance of being available if you walk up to it. That comes down to system reliability and availability modeling and analysis. That is outside the scope of this webinar. At this point in time, we're assuming that you have got a handle on the likelihood of your vehicle being available. Now, in the military context, you would have maintenance records, you would have all sorts of other things which should help you estimate availability moving forward based on historical data. If you don't, then that is also fine, and you need to do a theoretical analysis where you need to perhaps create a system reliability model and model how long it takes to repair things when things fail, take into consideration servicing, all those sorts of things. Now, that's just a high-level summary of the sort of thing you need to do, and this webinar is premised on you having gone through that to get to this stage of fleet planning. More than happy for you to reach out after this webinar to continue this conversation on email, but for the purpose of this webinar, we have to assume you've gone through that process. Larry George suggests that the slideshow shows that the probability that X is less than or equal to 8. Correct. Thank you, Fred. That answers your question, Larry. Job well done, Fred. So you can essentially see, Larry, that that blue column incorporates sort of 2 bars. The first bar, which equals that top step, is 9 to 10, and the second bar, or essentially exactly 10 vehicles being available, and that second step represents exactly 9 vehicles being available. So you can see that we include those 2 steps in that blue bar, which incorporates those 2 scenarios, 9 or 10 vehicles being available. But please keep asking those questions, because this confirms your understanding of what we've been talking about. All right, so the way you can answer this in a less painful way, as opposed to having to create a chart and then draw lines and stuff like that, is to again use our good friend Microsoft Excel. And here is the equation which allows you to calculate the probability that a certain number of vehicles are unavailable. So in this case, the difference between this equation, this formula, and the one you saw previously for the probability mass function is that the last argument, as opposed to being false, is now true. That simply changes it from a probability mass function formula in Excel to a CDF, or cumulative distribution function. All right, so let's go through some boring math symbology just to allow you guys to be aware of it when you see it in textbooks or reports. The CDF, the cumulative distribution function, is represented with the capital F followed by X in brackets, or the random variable in brackets. That's equivalent to the probability that your random variable is less than or equal to a certain value, which is what that term on the right-hand side means. And for all discrete random variables, it's simply the sum of all the probability mass function column heights up until that point. And so for our binomial distribution, it looks like this. Hopefully this is motivating you to go straight to the Excel formula and never, ever try and solve this one by hand. There's no reason to. Excel is really useful for scenarios like this. So this probability distribution we are looking at has that name, that binomial distribution, a sequence of what we call Bernoulli trials. Remember those trials we were talking about are scenarios where we have an outcome, one of two possible outcomes from an experiment. Toss of a coin is a great example. And so here is our probability mass function for a binomial distribution. Now, sometimes when it comes to fleet planning, we actually don't want to admire the number of vehicles we currently have, or the number of pumps we currently have, or the number of whatever it is your fleet comprises of. Fleet planning infers that you have some ability to control your fleet size. So perhaps as opposed to working out if we can launch a mission or not, we want to work out the fleet size we need to have so we are 100% certain that 9 APCs will be functional or available. That's fleet planning. That's the sort of fleet planning I'm interested in. How many vehicles do I need in total to be able to guarantee that I can launch my mission? So we've just gone through the process of, for a fleet of 10, we worked out there's a 73.6099% probability that if we select 10 vehicles, 9 or more of them will be functional. And the equation or formula we use in Excel to get that is 1 minus the binomial.dist of 8, 10, 0.9 followed by true. So 8 represents 8 or fewer vehicles being available. 10 represents the fleet size, 0.9 represents fleet availability, and true represents we are interested in the CDF. And we subtract that from 1 to give us a probability that 9 or 10 vehicles are functional. So this is the equation you use to work out the probability of a certain number of things being available. So what we can do is repeat this for a different fleet size. Remember, we are not happy with 73.6099% or 0.736099. We want to increase the number of vehicles we have to ensure that this gets to 100. Well, if we increase our fleet size, we change our Excel formula, and you can see that instead of there being a fleet size of 10, now there's a fleet size of 11. And we certainly have increased the probability of 9 or more being functional from 73% or 74% to about 91%. But we need to keep going because we need to be 100% certain we can launch any mission, any day, any night. And if we keep going, we come across a problem. That problem is that no matter how big my fleet size is, there is still a finite probability that all, in this case, 29 vehicles will be unavailable if I randomly walk up to 29 vehicles in the hope of being able to launch a mission. So even though the probability of that happening is really, really small, as you can see, the 9s, 0.999, all those 9s are starting to dominate the screen. So we're very close to a probability of 1, but it's still not quite there. And that means we can never guarantee that we will ever have 9 functional APCs. The reason why is failure is a random process. So if it's possible, there is a finite probability that that thing can happen. And it is possible for, if you have 100 vehicles on that particular day, it is still possible for 100 vehicles to be unavailable, even though it's highly improbable. So what we are going to do is deal with confidence. So instead of saying to your company commander, say, hey, look, this is a number of vehicles you need to have, be 100% certain you can launch a mission, you need to accept some risk that there's a chance that that won't always occur. Why is that? Because failure is a random process. And if we want to decrease that risk, we need to get a big fleet size, and that costs money. And obviously money, by definition, isn't free. Money is the antithesis of anything being free. So we can't give you 1 million APCs to make sure that probability of having at least 9 functional is as close to 1 as you'd like it to be. We need to compromise. So you need to tell me what risk there is that you're willing to tolerate of you not being able to launch your mission. And let's just say that company commander says, all right, I just want to be 95% certain that I can launch my mission. Well, we go through that process we just went through, and on the right-hand side of this column here, you can see the first value, which is greater than 0.95, 95%, is the one that is circled on the screen right now. And so this tells me that if I want to be 95% confident that I will have at least 9 APCs available or fully functional, I need to have a fleet size of 12. Now, if you walk up to another company commander and he or she says, hey, I don't want to be 95% confident. I want to be 99% confident. Well, the first value on the right-hand side, which is greater than 99% or 0.99, is this one here, which means that that company commander will need to have a fleet size of 13. So this is how we can start going about that wonderful process of fleet planning. How many things do I need? Well, the binomial distribution and the equations that we've just given you, which are all in the workbook. And this worked example is how you can tell. Okay, all right. So I think what I was getting to at that point was explaining how two different infantry commanders with different risk thresholds were able to tell me what risk they were willing to tolerate in terms of not being able to launch a mission, and that drove fleet size. The next thing I said was that, so if you got your own scenario, your own fleet of pumps, valves, vehicles, whatever it is, you can go through this exact process, this corresponding process, every step of which is in the workbook that you should have access to either now or shortly, for you to work at how many things you need in total to be relatively certain that a certain number of them are going to be available or functional. When I say relatively certain, another way of saying that is what risk you are willing to accept that they won't. So before I move on, are there any questions now, given that you can now hear me? Oh, good. Okay. Sorry about those technical difficulties. Very good example of how reliability touches every part of our daily lives, including webinars that have been planned for months in advance. Okay, so the next thing we're going to look at is that mission being launched. We've got 9 vehicles. They are happily trundling down the road or across the countryside. And some other logistician, some other supply guy, the quartermaster says, okay, how many spares will we need? How many spare road wheels do we need in particular? Now, APCs are just like many other vehicles, which do have, while they do have tracks, they also have wheels. And the tracks are wonderful at allowing them to go over all sorts of terrain. But these road wheels are very robust. They're not inflated. They usually have solid rubber tie around the outside. And these road wheels do deteriorate over time. Now, let's just say that the mean time between failure of these road wheels, in this case, is 12,000 kilometers. And we want to know how many spare road wheels do we need to take to get through a 2,000 kilometer journey. Now, I'm going to see that Pete has raised a question. We may want to mention that this assumes vehicles are independent. If there is a correlated issue, such as a common design defect or lack of fuel, the results will be very different. Thanks, Peter. Completely agree. If there's a lack of fuel, then you could argue that your vehicles are not available. However, in that scenario, I would suggest that most contemporary definitions of availability would still consider those vehicles to be available because they're fully functional. There's a term that we often use a lot to delineate between a machine working and scenarios where it's not getting power or not getting fuel or it's not getting input or throughput. So most contemporary definitions of availability would see those vehicles as available, even though there's a lack of fuel. Now, I do take your point. The infantry commander still can't launch their mission if there's a lack of fuel, but that's a separate problem. The other thing is that you suggested that these vehicles need to be independent. If there is a correlated issue, such as a common design defect, then they will not be independent. I do agree with that up until a point. In fact, I'm going to ask that we look at, if we look at that scenario, that idea of dependence, when we go through this road wheel problem. And Mahendra asked a question, or made a statement, I should say, where she said, wonderful if we increase availability to increase the odds of success instead of increasing fleet size. That's a wonderful observation. That's where reliability engineers can become wonderful value adders, because it's very expensive to simply give every company in a brigade or a division an additional APC to increase the likelihood of being able to launch a mission. Perhaps we can increase the availability by making it more reliable, optimizing servicing intervals, all sorts of other wonderful things which can improve the chances of us launching a mission. So I completely agree with you. I will say that we're sort of trying to, in this webinar, is focusing on fleet planning, given RAM characteristics being set in stone. But I take your point. We should never, ever give up the fight to improve reliability or optimize reliability, availability, and maintainability, because that saves money. So I completely concur. All right, so how many road wheels does this APC need, this single APC need, to get through a 2,000 kilometer journey? So in this case, there are 12 wheels. So there is, each one of those wheels will be traveling 2,000 kilometers in this 2,000 kilometer journey. So there's 12 wheels. Essentially, they're all traveling 24,000 kilometers in total. Now, the MTBF is 12,000. I know that's Fred's most favorite metric in the whole wide world. So let's assume that the MTBF is all we need, and that's going to be that's going to tell us that we are going to experience exactly 2 failures. Now, the reality is, regardless of even if we understood the time to failure of this road wheel using a normal distribution or a wireball distribution, it will still have an MTBF. I want to delineate, I want to make it clear that our friends and our colleagues on Ascendo advocate against using the MTBF as your only metric. Every random variable will have a mean value. So by definition, even if we know the time to failure model or probability distribution for this road wheel, it will have an MTBF. Well, let's just say we've gone through that process and we have an MTBF of 12,000 kilometers. These wheels are traveling 24,000 kilometers in total. Surely we can say with absolute certainty that we will have exactly 2. Remember, failure is a random process. So even though it's random doesn't mean it's not predictable. So instead of us being able to say there will be exactly 2 failures, we can say we would expect 2 failures. An expectation is a statistical term essentially analogous to the mean, the average. If we had 1 million APCs and they're all traveling 2,000 kilometers, and you average the number of road wheels that each one of those vehicles went through on that journey, the average would be 2 based on our information we already have. So, but remember, failure is a random process. We can't just deal with the expected or typical values for anything. So again, if we say X, uppercase X, is the actual number of road wheel failures, then we need to examine the probabilities of different numbers of road wheels failing. So in this case, there's a chance that 0 could fail, there's a chance that 7 could fail, there's a chance that 2 could fail. So we need to do what we did for our APC fleet planning example and work out individual probabilities of certain numbers of road wheels failing. And so we're going to go back to that probability mass function. But we're not dealing with the same process anymore. We're dealing with a completely different process, one where our road wheels are failing over time or over usage or over distance. We're not dealing with trials. We're not going up and touching an APC just to see if it's working or not. So the equation for the probability mass function of this random variable, the number of road wheel failures that we're going to experience, is this expression here. And this is a little bit complicated to solve. And it incorporates the expected number of failures, which we've already worked out is 2. And if we substitute in for X, we will work out exact probabilities of certain road wheels failing. And this is called the Poisson distribution. So if you're ever doing spare planning or sparing analysis, and someone says, well, we're going to use a Poisson distribution, that's where it comes from. It comes from this process where we are going through a certain number of spare things. And the Excel formula you need to use to work out the probability of exactly a certain number of things or certain number of road wheels failing is this one on the screen right now. Okay, so let's take this knowledge and create our chart again, the probability mass function. But in this case, the random variable we're investigating is the total number of road wheel failures. And we use that probability mass function equation using Excel, we get these columns here. And we can see that there's a clear clustering of likely values around 2. But as he pointed out, you can still see there's a little column around about 6. So that means there's a chance that we could have 6 road wheels fail on our journey. In fact, there's a probability that more than 6 have failed once we more than 6 will have failed for each vehicle. Now, Doug is asking the question, how many kilometers have the road wheels already traveled? That will also influence how many spares will be needed. Great question, really good question. I'm going to come to that in a minute. So in the same vein as the conclusion we came up with for our APC fleets, where we could never have a fleet size big enough to guarantee that 9 will be functional, we can never guarantee that we'll have enough road wheels to get through our journey. So how many road wheels do we need on our APC? Well, this is where that cumulative distribution function becomes very handy again. And here is the Excel formula you need to use to calculate the the CDF value. And we replace these columns with those lines, which help us create this little step thing here. And so if I want to be 80% confident of making the journey, well, I simply plot across here and it tells me that I need to have 3 spare road wheels, or at least 3 spare road wheels. And if I have 3 spare road wheels on my APC, that tells me there's an 80% chance of me making it through my journey, being able to replace all those road wheels that are going to fail. If I'm not happy with that, if I want to be 95% certain, then I need to have 5 spare road wheels. So again, it comes down to what risk are you willing to take? You can never be absolutely certain that you will have a fleet size big enough to accommodate all scenarios, or enough spares to guarantee that you will have enough to get through a journey like this. Now I'm going to come back to Doug's question, how many kilometers have the wheels already traveled? That will also influence how many spares will be needed. So, and I can see that another attendee has also asked how many non-operating road wheels can the APC tolerate? Maybe they should get an AAA roadside assist account. Completely agree, Fred. I'm not sure of AAA's roadside assistance packages for Afghanistan and other likely areas of operations moving forward, but hey, I'm Australian, maybe there's a little bit more robust coverage policies that I'm used to compared to where I come from. So we'll go back to Doug. The amount of kilometers that the road wheels have already traveled will be a factor. And to a point, that's 100% true. However, when we are dealing with these scenarios, we can be sneaky. And the fact that, for example, one of those road wheels on that APC will be almost brand new, and another one of those vehicles will be, one of those road wheels will be close to death. We can bring it back to that wonderful metric that Fred really loves, the MTBF, because that dispersion in residual useful life of those road wheels is essentially, in a way, averaged out. And there's a statistical phenomenon behind that. And so it essentially means that if we assume that each one of these road wheels is at a random point in its useful life, then those 12 road wheels acting together, in essence, if there's enough of them, will behave as if there's a constant hazard rate. So if you have thousands upon thousands of things that are within your system and are all of varying ages, that's where you do experience what's called a constant hazard rate when it comes to spares and spare analysis. But, and here's the but, the MTBF is not reliability. At best, in this scenario, the MTBF can be used for logistics sparing. And the problems arise when we have a really small fleet. So for example, if our APC only had one road wheel, then of course the age of that road wheel at the start of the journey would have a huge impact. And we cannot assume that because there are 12 and their residual useful life are essentially randomly spread, but each one of them still has an MTBF of 12,000 kilometers. We cannot simply assume that away. And that's one of the biggest problems I see when it comes to sparing analysis, because the Poisson distribution is based on the assumption that things fail at a constant rate. And that's okay if you have a relatively big fleet size, if your vehicle has lots of wheels. But if it doesn't, if you've got a small number of small fleet size, you're expecting to go through a relatively small number of spares, then that's where you really need to understand the reliability of the thing you are replacing. And when you do that, you can actually realize, through some of my other webinars touch on this, you can actually realize that you need a lot fewer spare parts, especially if you start off with brand new things. But hopefully that answers your question. Yeah, Drennick's theorem. Thank you for putting a name to that concept. Drennick's theorem, essentially, I think Drennick was originally talking about submarines, essentially saying that, hey, if all the submarine parts have randomly progressing through their residual useful life, the entire system will act as if it has a constant hazard rate, which is an easy get out of jail free card in terms of doing more robust or more proper statistical analysis when it comes to reliability. And there are some cases where that's true, but don't forget, things like submarines, they go through deep maintenance periods. And so to suggest that when those submarines get put to sea, they're essentially all randomly traveling through their own journeys on the residual useful life scale, that is just that is a fallacy at best. Yeah, so Fred points out if the APC can run on 4 bad wheels, then the math gets a bit more complex, yet the process to sort out the spares pretty much remains the same, which is a great point. It means that we can still work out how many things are failing, but if we only need to have, we're still expecting, if we have all 12 wheels functional, we'll still expect 2 to fail on our journey. But if we only need 8 to be fully functional, then we can use the equations we just learned to work out the probability of making it through our journey. People who want to talk about that further, we are running out of time, so you'll have to reach out after this webinar is completed. So it comes down to the risk you're willing to take. So just to summarize the 2 discrete probability distributions we went through today. The first one was a binomial distribution. Models a number of successes you see for a given number of trials, and Poisson distribution models a number of events you see within a given interval. So we use a binomial distribution a lot for number of available or functional systems, single shot systems testing, because we often do, for example, screening testing, where if a ball bearing has a certain defect, then it gets discarded. If the defect within tolerances, it gets accepted. Another example of binomial distribution modeling that process. And the Poisson distribution is often used for spare parts prediction and unfortunately for MTBF testing because it is based on the assumption of a constant hazard rate. Now, MTBF testing is a whole new kettle of fish in terms of so-called reliability demonstration testing. I'm not going to touch on that today in great detail, but it is not. We do a lot of MTBF testing, but there are lots of issues with that, with the assumptions that we often make. So to summarize the summary, the binomial distribution in our example today was used to work out how many vehicles are available, or the probability of certain numbers of vehicles being available, I should say. The Poisson distribution helped us work out how many spare road wheels we need when we're going through a mission based on the assumption those road wheels are going to be failing at a relatively constant rate. So, a couple of really good questions and comments through in today's conversation. Are there any questions about discrete probability distributions? Noting I've only covered 2 of them, but they are without a doubt the big 2 in the world of reliability, logistics and sparing and fleet planning. Any questions or comments? After this, I'm going to model the availability of my fleet of microphones for webinars. See what I come up with. Call that Jackson's theorem. Yes, for me, user error is always included because it's a dominant failure mechanism for most of the stuff I'm involved with. Thank you, Larry. So while people are typing any final questions or comments, just want to remind everyone that feel free to not just reach out in regards to specific topics. If you have a comment or a query or a request or a conundrum that perhaps we could address in webinar form moving forward, please feel free to reach out. Thank you, Patricia, and thank you, Nathaniel. Please feel free to reach out. We're always trying to respond to suggestions from you guys as well. We're trying to remain topical. We're trying to remain hip hop happening in contemporary. So if you have any ideas about what we can do moving forward, please feel free to reach out. Maybe we'll address that in a podcast. Maybe we'll address it in a webinar. But thank you very much, Mahendra. Fred is sharing a message about the workbook. As you are well aware, Sendo is still in the process of upgrading its website. So there's still a couple of things that Fred is bolting down right now, but that workbook should be available. So Doug asks, are there any resources on Ascendo or Speaking of Reliability podcast for the calculation of availability question that was asked earlier? And the answer is yes. It is a broad problem or broad question you're trying to answer. So it will involve both system reliability modeling and downtime modeling as well. It's one of those things where I think it would be best answered in a course or you'd have to do a bit of study. But yes, if you looked at system reliability modeling, that will help you understand how you can model systems up until the point of failure. And of course, there is maintainability stuff you can look at in terms of modeling what happens after things fail. And then I would suggest perhaps if you can't find the resources you're after, again, feel free to reach out via email or have a chat. Nathaniel asks, can you do a talk on the RAM of fleet vehicles? Could you just clarify that a little bit, Nathaniel? Are you talking about, what are you talking, because there's so many things that would be within the remit of the reliability, availability, and maintainability of fleet vehicles. Preventive maintenance, is that what you're referring to, Kenneth? No worries, Doug. Tracking and measuring real data. Okay. Nathaniel, if you don't mind, could you send me an email with a few more details on that one? For example, I have done webinars where I looked at servicing interval optimization for a fleet of military vehicles. They were the Land Rover 110. In that scenario, that analysis uncovered the fact that we were servicing way too often, and by servicing less often, we were able to increase the reliability. So that's one thing. But again, if you could reach out and maybe we could start a conversation about what it is you're after, that'd be very useful. Nelson said that, just coming back to the applicability, so we can get away with the MTBF as many items together will approach a constant rate of failure. Yes, if those many items all start off with essentially random ages. If they all brand new when you start, then you might have a problem. But if they're all if they're all at varying ages or progressing randomly through their service lives, then the constant rate of failure for lots of widgets is a pretty good assumption to make. You can all but guarantee you'll see a constant hazard rate above 30, fleet size of 30. And depending on the nature of failure, that assumption is valid for smaller fleet sizes or smaller numbers of things you're repairing. Thanks for sharing the email as well, Fred. So if anyone does want to reach out, of course, assume that if you got to Ascendo Reliability, you can find my contact details. But if for those of you who want to save those 30 seconds, my email address is in the comments box, the chat window, I should say.